Hello, I'm Sebastian. I'm a graduate research assistant at the Autonomous Vehicle Systems Laboratory, and today I'm going to be presenting on characterizing electroadhesion in vacuum, experimental and simulation frameworks for space docking. So what is electroadhesion? Electroadhesion is a method to dock electrostatically with a electroadhesion pad to a substrate material. Um, This is done by generating electrostatic forces at the interface between the substrate material and the electroadhesion pad. An electroadhesion pad is basically nothing else but two electrodes immersed in a dielectric. And by applying positive and negative high voltage to each of these two disconnected and mostly patterned electrodes, you can generate an electrostatic force with virtually any material. Um, as I said, this works on dielectrics and conductors, both by realigning charges within the material in the conductor. The charges can freely move and completely realign, while in the dielectric, you only have polarization. However, it works on both materials, better on conductors and less well on in dielectrics. There's multiple ways to construct electroadhesion pads that are shown on the right. And the most common one is, as I mentioned before, a two electrodes immersed in a dielectric and placed onto a substrate backing material. You can, however, construct electroadhesion pads depending on the application in many different ways. So why is electroadhesion interesting for space applications? Well, first, electroadhesion is material agnostic within the limitations that I just described, that it works better or less well on different materials. However, this is very interesting in space because your satellite is made from many different materials and it would work on any of these surfaces. Second, it is conformal in the sense that electroadhesion pads are flexible and can adapt to any type of satellite shape and generate the force that you would like. It is also a low mass and low power system because you only have to apply a static high voltage, and those electroadhesion pads are very light. Therefore, it might be very good for soft docking applications and detumbling applications. The detumbling application is shown in the video on the bottom right. It's basically just a satellite surface brushing against an electroadhesion pad, generating a friction force, and that slows down the tumbling rate. It works on any type of unincorporated target, and also it works in vacuum. However, this has not been quantified well, how it works in vacuum and if it works better or less well than atmosphere. Most of the work on electroadhesion has been in terrestrial robotics, so in atmospheric conditions. To give you a short literature review on the subject, there's 30 plus known parameters that influence electroadhesive forces. They range from the voltage you apply to the electrodes, to electrode geometry, to dielectric properties, to substrate properties. So there are many different factors that have been identified. Electroadhesion is also inherently dynamic in nature. That means there is a time varying response. If you turn the pad on, the force doesn't directly develop. It needs some time to charge up the pad and polarize the dielectric. And that also means when you turn the voltage off, the electroadhesion force doesn't appear right away. There will always be some residual electroadhesion force. And third, multiple studies have focused on the force directionality. That means depending on if you're applying shear force, normal force, or a torque, electroadhesion works better or less well. And there are many quantitative studies as to how it works for different materials, which is shown on the bottom right. And a lot of this is also related to surface conformity, just because the pads adhere or like have better surface conformity depending on how rough the material is. So the main gap when it comes to electroadhesion is vacuum performance, because most of the work that has been done on electroadhesion was in atmosphere. It is known that humidity, one of the main atmospheric factors that we have, strongly and negatively affects electroadhesion performance and lowers the force that we can see. So now this leaves the question open: what vacuum like how vacuum would affect electroadhesive forces. Is it going to make them stronger? Is it going to make experiments more repeatable? Because many terrestrial experiments have suffered from very low repeatability due to the varying environmental conditions. But also, might it increase residual polarization on the pad and complicate de-adhering from the pad, as I had shown before, since there is a time dependence. So our work focuses on testing electroadhesion in a vacuum system, and that is needed to better assess its feasibility for space applications. So for our experiments, we started by manufacturing our own electroadhesion pads. We focused on two standard geometries that have been proposed, one interdigitated design, which is shown on the bottom, and one spiral design. And we also used two different manufacturing processes and tested a novel dielectric coating, which is known to be a very crucial factor for electroadhesion performance. Then we did COMSOL finite element simulations. This is the standard approach to simulate electroadhesion pads. It should be noted, though, that the agreement from previous studies has been very limited, as it is close to impossible to simulate all the 30 plus factors properly in COMSOL. And our work has been uses COMSOL just as a baseline to compare to experiments, and we do not use COMSOL to inform our electrode geometries or change anything about our pad design. It is more to see how well we can match it to the pads that we've actually manufactured. Then this work was conducted in collaboration with In-Orbit Aerospace, and they built a test setup that could test shear and normal forces in atmospheric conditions. And then this is complemented by laboratory experiments at the Autonomous Vehicle Systems Lab at CU in the Eclipse vacuum chamber, where we first baseline the performance of our electroadhesive pads in atmosphere and then conduct vacuum experiments to compare the performance that we can find. And we also test and compare both pad designs. So the standard way of constructing an electroadhesion pad is using flexible printed circuit boards. This means we have the two electrodes sandwiched in between two copper sheets, and there's some adhesive that is holding this all together. So what is known for electroadhesion pads is that we would like to get coating materials that have very high dielectric strength to apply very high voltage and generate a stronger force, but they should also have high permittivity to let the E fields through. Kapton excels on the dielectric strength, however, does not have the high dielectric permittivity. However, this is the simplest and cheapest option to mass produce electroadhesion pads. The second design, which has been recently proposed, is aiming to address these material limitations. There's no single material that excels in dielectric strength and dielectric permittivity. So this concept proposes to use a bilayer design. First, use a baseline layer, first bottom layer that has strong dielectric strength, which is typically a polyamide, and then use a secondary layer that has very strong or very high dielectric permittivity, a polyurethane. So we had coating experts at the Laboratory of Atmospheric Science help us to build and manufacture such electrodes. The process that we used is we had a Kapton backing, micro-etched copper electrodes, chemically etched, professionally done by a company, and then had the experts at LASP spray coat this electroadhesion pad, first with a polymatte primer and then a polyurethane coating. The result is shown on the right. And the computational study that proposed this design has found these pads to have superior performance, but it was never experimentally tested. So looking at the COMSOL results, we used the standard approach, the AC/DC module in COMSOL, and a Maxwell stress tensor to predict normal forces for our pad design. So we input exactly the geometric parameters that we had in the manufactured pad to have best comparability with experimental results. COMSOL is not able to predict shear forces. As one can see, the EA normal force strongly scales with applied voltage at the pad. And typically, and in most experimental studies, the voltages that have been applied to the pads range from 0 to 5 volts. However, it can be seen that it is should be very advantageous to apply much higher voltages. And we did stress test our electroadhesion pads and see where they arced. And we could apply voltages up to 18 to 20 kilovolts for both the FPC printed pad and the bilayer pad. So yeah, this just allows us to test to way higher ranges than has been previously done, and we expect to see higher electroadhesive forces. So this is the atmospheric shear force and normal force test stand. In this case, on the photo configured to test shear forces, one can see the force sensor, the electroadhesion pad, and the paper substrate in this case that's being pulled on. So yeah. For the atmospheric results, we tested both shear and normal forces, as I said before, and one can see that shear forces, and that is consistent with previous studies, are much stronger than the normal forces. In orbit, tested multiple different pad configurations, and as you can see, they all perform differently, but they all show the same trend that going to higher voltages increases the electroadhesive force that you're measuring significantly. The whether the rate is exponential or linear differs between the pads, but it is important to note that the shear forces we have seen are much higher than previously in previous studies. But this also is due to us applying higher voltages than those previous studies. Then we also looked at the normal forces that are much smaller and compared them to our COMSOL simulation, because COMSOL can only simulate normal forces. We can see that there is good agreement within an order of magnitude. However, the exact trend differs, and it can be expected from what we're seeing here that we will not see as much of an increase in normal force at higher voltages as COMSOL predicts, because the trend that COMSOL predicts here over this range is much steeper. Then we also looked at how the geometry influences the results. We tested the spiral design and interdigitated design, and we saw that the interdigitated design performs better than the spiral design, which is not in agreement with previous computational studies, where the spiral was predicted to show slightly higher electroadhesive forces. But again, this is way less pronounced than the effect that a higher voltage has on the achievable electroadhesion force. We also conducted tests on how the pads perform for different substrate materials. And as one can see, it works significantly better on the conductors, aluminum and copper, than on the paper substrate, which is consistent with theory and prior experiments. Now going to the vacuum tests. It is very difficult to build a vacuum test setup that is fully vacuum compatible in terms of materials, in terms of the actuators, and also can be fully remotely operated. We chose to use a rotator test setup where a sample is placed onto an electroadhesion pad and then uses gravitational preloading. And then we apply the voltage and rotate it by ideally 180 degrees in the vacuum chamber. We can deduce from the rotation angle where the sample falls off what the maximum shear and normal forces that we can get from this electroadhesion pad are. And in general, the higher the rotation angle is, the closer to 180 degrees, the better the performance, and the higher the achieved electroadhesion forces. We recorded the results for these experiments in the following table, where we had different samples, in this case aluminum, of different weights, ranging from 0.5 to 42 grams. First, we baselined the performance, meaning that we just placed the sample onto the electroadhesion pad and rotated to see how much natural friction force there is between the pad and the sample. As one can see, the lighter samples require way less voltage to complete the full rotation than the heavier samples. There's some variability within this. All of these tests were performed in atmosphere, and this is the atmospheric variability that I was talking about, and also probably related to how well the surface contact between the sample and the electroadhesion pad was in these experiments, which might differ just due to the mechanics of gravitational preloading. If you preload directly and by applying a force before, you get much better surface attachment than just from gravitational preloading. As you can see, the 42-gram sample could not complete a full rotation in atmospheric condition. this is why we repeated the test under vacuum conditions and only applied 8 kilovolts in this case. And the sample rotated to 180 degrees without any problems, showing a stronger electroadhesion force. And interestingly, after turning off the voltage, it stayed on for 12 plus hours, while previously lighter samples had fallen off almost immediately after turning off the force. So that points to residual polarization being much higher in vacuum or much more pronounced. We also investigated surface conformity, which is another factor that we found to be very crucial during the experiments. We used materials of different rigidity levels, ranging from aluminum foil, which is super conforming and flexible, to an aluminum plate, which is rigid. And we found that it is much harder to generate an electroadhesive force if the surface conformity isn't close to perfect. And then we tested preloading on the rigid body, and that increased performance by quite a lot because we forced surface conformity between the plate and the electroadhesion pad in this case. Then we repeated those tests with the bilayer pad. And what's important to note is that the bilayer pad showed very high baseline stickiness just from the coating process, and the coating material was just sticky in general. So it is more difficult to directly compare these results here that we have, the rotation results, to the previous results. However, in general, the bilayer pad performed slightly less well than the other pad. What was consistent, though, and what is important to note, is that we retested an aluminum plate, an aluminum sample, and a dielectric sample, in this case, polyether ether ketone, both in atmospheric conditions and vacuum. And in vacuum, all of these 3 samples performed significantly better, and we saw a higher electroadhesive force. And on top of that, we also again saw more remaining residual polarization because we did not have immediate deadhesion. To sum up what we've learned from these studies that is relevant to using electroadhesion in space and just general spacecraft docking, electroadhesion is stronger and more repeatable in vacuum. This is presumably due to eliminating environmental factors like atmosphere. Moreover, shear force dominates over normal force. This means for most space docking concepts, they should be designed, the actuators, to exploit shear loaded interfaces like the tumbling one instead of normal forces. We also found that surface conformity is critical, and this is typically achieved in terrestrial applications by preloading. This is complicated in space because, especially for soft docking applications, you have no chance to preload it. And this is just something to keep in mind when designing these systems, that this might be a bottleneck. From our studies, what we found is that the applied voltage is much more important than the electrode geometry. So we believe that it would be much more interesting or much more important to design these systems for a higher voltage instead of trying to optimize electrode geometries, because they don't play as much of a role. And then in terms of challenges, deadhesion mechanisms and residual polarization remain a large issue because we cannot actively undock from an object without any mechanical actuators at the moment. There's no electrostatic version to force undocking, and we have seen that this residual polarization is much increased in a vacuum environment in our experiments. And lastly, it is important to characterize space environment effects like atomic oxygen, radiation, etc., on the materials that are used, the dielectric materials. Our sponsors have performed some TVAC tests that show promising results, but there is more testing that needs to be done and more work on investigating how the space environment affects electroadhesion. I would like to thank the United States Space Force for supporting this project, and we'd also like to thank Glenn Etzinger at LASP for his help in realizing the bilayer coating. Thank you very much for your attention.